Toom-Cook fast multiplication algorithm is a generalization of the famous Karatsuba algorithm. In this video, I'll try to provide a simple explanation and visualization of both, especially Toom-Cook 3 or Toom-3. So let's say you want to multiply 1, 2, 3, 4, 5, 6, and then 7, 8, 9. That's a 9-digit number by, say, another 9-digit number. Let's say 8, 7, 9, 6, 4, 5, 2, 1, 3. Alright, so traditional method of multiplying, the grade school multiplication, requires picking one digit at a time from one number and then multiplying one digit by one digit for all 9 digits in the other number. So for example, in this case, 3 times 9, you write it here, 3 times 8, and 3 times 7, and you keep doing this up to the most significant digit of the upper number, which is then 3 times 1. So you have one row with 9 single digit by single digit multiplication. You keep doing this for the rest of the numbers. So if you do so, next one is 1, and of course it becomes 0, so you shift 1 times 9, and then 1 times 8, upper numbers. So, and then you keep doing this, and finally we get to, say, 1 times 1 on top. And you continue doing this. Of course, you end up with 9 rows, and in each row we will end up having 9 single digit by single digit multiplication. So overall, as expected, we end up with 81 such multiplication, and we are not considering additions that are required, of course, in terms of computation of complexity, because they are not comparable to the complexity of multiplication. They are much simpler than multiplication. So as a result, the complexity of this operation in terms of finding the result of it is a big O of n to the power 2, or basically in this case 9 to the power 2, or 81 multiplication, single digit by single digit. So naturally the next question is, okay, if we visualize that, which is this, what this black curve is doing here with the dots, on x-axis you have number of digits. For instance, in this case we have 9, and you can see that the black dot here indicates 81 multipliers needed on the y-axis. So you can see that the complexity of multiplication is growing by n squared, hence the complexity of big O of n squared, and it's exponentially growing when you get to, say, number of digits around 30, n equal to 30. Then as the dot is indicating on top, you can see that it says we are dealing with 30 to the power 2, 900 single digit by single digit multiplication. So the next question naturally is, how do we simplify this? This is too much. Or basically in the O(n squared), how do we manage to reduce this power of n? Can we reduce it to, say, n to the power 1.5, 1.6? That's what the Karatsuba and the generalization of a Toom-Cook algorithm achieve. So in case of Karatsuba, which is also a special case of Toom-Cook, when we set the parameter of Toom algorithm to 2, or basically Toom3 Algo, in that case, as explained in a separate video that covers Karatsuba algorithm example, we get to big O of n to the power 1.585, which is coming from effectively log 3 base 2. That's exactly what equal to 1.585. So that is the big O complexity of Karatsuba that is shown or highlighted in blue curve. As you can see, for the Karatsuba or Toom3, it's substantially reduced complexity compared to traditional method. So this is traditional or grade school method. So in this case, Karatsuba, you can see that when we get to 30, as n to the power 1.585 indicate, you're talking about roughly on the order of, say, 220-ish or 215, between those two type of number of single digit by single digit computation complexity, which is substantial reduction. So what Toom3 as an extension of Karatsuba achieves is further improvement. It gets to big O of n to the power 1.465, and that is coming from again log 5 base 3 and visualizing it so that you can see what's going on is the red curve here. So you can see that there is a further reduction, though not as substantial as initial reduction, from Karatsuba to say Toom3, extension of Karatsuba, which is also referred to as Toom2. So in the case of Toom3 for n equal to 30, you can see that now we are talking about this point on the y-axis indicating on the order of, say, maybe 140-ish, roughly, complexity, instead of the 215-ish for the Karatsuba. So again, when we get to large numbers, large multiplication of large digits by large digits, we see that there is a non-negligible reduction in complexity when we migrate from Toom2 to Toom3, from Karatsuba to Toom3. Okay, so that's the incentive. And if you want a sort of zoomed in version to see better, it's this one plot here shown. So this plot is just the top plot, but except I removed the traditional method and only focused on Karatsuba Toom2, Toom-Cook, and then we have Toom3 or Toom-Cook 3. The same thing as I mentioned above, just the focus version, zoomed in version of that plot. Okay, so let's focus on the Toom3 algorithm or Toom-Cook. As I said, Karatsuba is discussed and an example of that provided in detail in a separate video that the link is provided in the description of this video as well. But here is the example to illustrate in a simple fashion how Toom3 or Toom-Cook 3 is working. Just bear in mind that in general, before I jumped into the example, the generalization of Toom-Cook algorithm is not limited to just Toom3. Toom-K is the generalized scenario with a parameter k, and it is shown mathematically that the complexity is on the order of O(n) log 2k minus 1 base k. You can see that when you substitute k equal to 2 to get to Karatsuba or Toom2, you get exactly log 3 base 2. If you substitute k equal to 3 for Toom3, which we are going to cover an example here, then this exactly becomes log 5 base 3. Okay, so for Toom3, focus on the example that I have provided here. So the two numbers, n1 and n2, I'm going to write them here like this. As I said, my goal is achieving a simple explanation. So n1 is 1, 2, 3, and then you can see that I'm just rewriting the number n1 in the form of 1, 2, 3 times 10 to the power 6 plus 4, 5, 6 times 10 to the power 3 plus 7, 8, 9 as it is. Okay, for n2, I am going to write it exactly with the same style. So I have 8, 7, 9, 10 to the power 6, 6, 4, 5, 10 to the power 3, 2, 1, 3. Now let's play this trick or game that we refer to, say, 10 to the power 3 as x. And of course 10 to the power 6 becomes x squared naturally. So therefore my number can be written as 1, 2, 3 x squared plus 4, 5, 6 x plus 7, 8, 9, and also 8, 7, 9 x squared plus 6, 4, 5 x plus 2, 1, 3. Okay, what's the benefit of this? We haven't yet achieved anything. I mean, we haven't improved anything. It's the same 81 multiplier as before. Well, the trick comes after this one. All right, so let's go ahead. We were doing this multiplication as before. So the job is n1 times n2. These are the two polynomials that we later substitute x with 1000 or 10 to the 3. So if we do so, and if we write this whole thing, what we end up is 1, 2, 3 times 8, 7, 9, and then we get x2. So I want to refer to these numbers, just to simplify description, as A, B, C, D, E, F. So what I'm going to do is I'm going to refer to this 1, 2, 3 as A, 4, 5, 6 as B, 7, 8, 9 as C. And I'm going to refer to 8, 7, 9 as D, next one as F, next one as E, and then the last one as F. There is nothing wrong with that. So when I multiply n times n2, what I get is this situation. I get AD, so A times D, naturally times x to the power 4, so times x to the power 4 plus. Alright, the next one that I get here is A times E x to the 3 plus D times B x to the 3. So I get A times E plus B times D, doesn't matter. So these are the only ones that can generate x to the power 3, or they are coefficients of x to the power 3. Okay, so what about x to the power 2? Fine. For x to the power 2, I have three things that can generate that. A times F. Next one is the two center terms, B times E. And finally, C times D. These guys can generate x to the power 2. Okay, what about x? Well, that's easy. B times F. So B times F can generate that for me. So I'm going to do B times F plus, and of course, E times C. All right, so that generate x. And the last number, of course, is just C times F, these two things that I need to multiply. So I'm going to just write as plus C times F. Okay, what's the use of it? We haven't yet achieved anything. Still, we need this way, still 81 multiplier. Well, what comes next is the achievement. So, which is the interesting thing or technique that Toom did back in early 1960s, and then a few years after that, Cook sort of refined it, and hence it became Toom-Cook Algo. So let's define a new variable x0 as, I'm going to name these guys. So let's name CF as coefficient 0, C0. Let's name BF plus C as coefficient C1, corresponding to x to the power 1. Let's name this one here as C2, corresponding to x to the power 2. Let's name this one as C3, corresponding to x to the power 3. And the last one here, AD, as C4. So I'm going to define x0 as a new variable, just simply equal to C0, which is CF, so which is, of course, C times F, a 3-digit by 3-digit. Let's not forget C here is a 3-digit number and F is 3-digit number. So for this one, we need to compute 3 by 3 single-digit multiplication, or basically 9. Okay, so let's forget about that for now, but that's CF we need to compute to get to x0. Okay, what is the next one? The next one is x1, that I'm going to define it this way. I'm going to say C4 plus C3 plus C2 plus C1 plus C0. I'm going to define x2 C4 minus C3 plus C2 minus C1 plus C0. And two more. I'm going to define x3 as 16 C4 plus 8 C3 plus 4 C2 plus 2 C1 plus C0. And finally, the easy one is the last one, gonna be x4 equal to, and this one is gonna be C4, and these are the five new variables that I have defined, in which C4 and C0 are straightforward. C4 is just AD, as you can see here, so I'm gonna put AD here. and that's for x4, and x0 is CF. Okay, what's the benefit? Well, there is one important benefit here, and I'm going to change the color so that you can see it easily. This x1 here effectively can be obtained, this whole thing that I said, the five coefficients C0 to up to C4 added together. You can actually get it by doing this calculation, or let's say multiplication. A plus B plus C, each of these, as I said, A, B, C are single digit, are 3 digits, as we name them, times D plus C plus D plus E plus F. The next line, which is x2, as I said, this sort of a linear combination of C0 up to C4 is simply A minus B plus C times D minus E plus F. Again, A, B, C, D, E, F are 3-digit numbers. And this last one here is simply can be obtained or computed by multiplying 4A plus 2B plus C times 4D plus 2E plus F. Okay, now this is the key. So what happens is this one. Remember I said this A, B, C are 3-digit numbers. This D, E, F are 3-digit numbers. You add 3-digit by 3-digit numbers, you end up with at most a 4-digit number with the most significant digit in the 4th digit being 0, 1, 2. So it's very controllable. When you multiply these two numbers, you're dealing with a limited complexity of as if you're multiplying, say, marginally. Again, sort of just marginally for the sake of this conversation. So the whole thing about this simplification is asymptotically we are simplifying. So it's as if we are multiplying another roughly 3-digit by 3-digit to get to x1. So you don't need to compute. What I'm trying to insist on is we are not computing C0, C1, C2, C3, C4 and adding them together to find x1. What we are doing is we are computing this thing written here on the right side, because that translates to compute it. We just need to do effectively asymptotically just a simple roughly 3-digit by 3-digit computation. The same thing about next line. To find x2, we are not really finding C1, C2, C3 because those are not helping us, and we are just computing this multiplication shown on the right side. That is following the same logic. It's asymptotically roughly a 3 by 3 on the order of a 3 by 3 digit, let's say single digit multiplication. Okay, and the same thing for x3. We can rewrite it this way, and it's on the same ballpark roughly. So the message or the method is this. With the formation of these 5 new variables as a function of the coefficients C0, C1, C2, C3, C4, we are effectively just dealing with 5 3 by 3-digit multiplication that I am showing in red color. Or if you want it to be further highlighted, I'm going to highlight them with a different color. So I'm going to highlight them with green color. So this one, this one, this one, and this one. These are the 5 3 by 3-digit multiplication that we need to deal with them, literally compute them, so that we have the value of x0, x1, x2, x3, and x4. And as soon as we have them, what is the benefit? Sure. So the message that we have up to this point is we sort of avoided the scenario of 9 3 by 3 multiplication that traditionally we had to do to get to n1 times n2 computation. So rather than doing 9 3 by 3 single digit computation, we are doing 5. So 9 multiplication, 3 by 3 digit each, is now reduced to 5. But we are not yet done, so what? We still don't have these C0, C1, C2, C3, C4 roughly. Well, we do. We have from x0 that is computed, effectively CF is done. x4, I'm counting among the 5 multiplication that we just have to do no matter what. So x4, C4 done. And x1, x2, x3, believe me or not, it's actually done as well. How? There you go. So so now at this point, since we computed the 5 3 by 3 multiplication already, we have x0, x1, x2, x3, x4 values available. As a result, we have C0 available and C4 available as well. The only thing that we still don't have is the value of C1, C2, and C3. All right, so let's do this. I'm going to just add x1 and x2 together, the lines number 2 and 3. If I do so, you can see that C3 negative and C3 positive cancel out, C1 negative and C1 positive cancel out, and then as a result I get 2 times C4 plus C2 plus C0, which if you reshuffle things around, the only unknown is C2, by the way, in here, because we already know that C0 is X0 and C4 is X4, so we have C0 and C4. So we get C2 is equal to, I'm going to write it this way, X1 plus X2 divide by 2 minus C0 minus C4. We have C2 as a result, because as I said, we are in the process of doing or consuming this 5 multiplication needed. We already have x1, we already have x2, we already computed C0, we already computed C4. The only little thing we need to do is a sort of a near trivial divide by 2 multiplication division, which is need to be considered as a part of complexity, but it is nothing compared to the overall reduction, especially for large numbers. So C2 is computed this way, and the only now we have to move on to the next things we have to do. So the same process can be repeated in the sense that now we can move on and use a combination of, say, for instance, I can play the game of do the x3 minus, let's say, for instance, let's say we can get rid of C1 and keep C3 as a result. For instance, I can say 2 times x1. If I compute this, again, I have x3 and I have x1 via the 5 multiplication that I did. So if I compute this, then I end up with 16C4. I end up with, just to make sure I'm not missing something, so I end up with this situation. I end up with 14C4. So I am keeping x3, and I am just subtracting the 2 times x1, and I end up with 14C4, and then I end up with, let's say, 6C3 and 2C2, and C1 cancel out, 2C1 and negative 2C1 cancel out, and then I end up with negative C0. So the message here is, again, we have the value of x3 minus 2x1 computed available. We have the value of C0 available, C4 available, C2 available here, I just computed, and the only unknown is C3. And the rest of the process is sort of straightforward in the sense that the number of computation needed here is minimal in terms of additional complexity, because 14 can be written in the form of 10 plus 4 times C4, and 6C3 can be written as 10 minus 4. So effectively what I can say is this one is 10 times C4 minus 10 times C4 10 times C4 minus C3 plus 4 times C4 plus, let me just make sure I'm not missing something. So I'm talking about plus 10 times C4 plus C3 plus 4 times C4 minus C3. And then 2 times C2 minus C0. The reason I did it this way is this 10 is not a multiplication. You just add C3 and C4 and you end up with the result. But anyways, this is illustration to show you that the minimal trivial amount of additional multiplication here is negligible, and the only unknown is C3 that is solvable here. And then from there we can just fit all the numbers, or let's say substitute all the numbers in one of the line and find the only remaining unknown, which is then C1. So C3 is found, then C1 is found. As a result, this is just a simple description or clarification that why in Toom3 algorithm or Toom-Cook 3 people state that the total 9 multiplication of 3-digit by 3-digit is reduced to 5 3-digit by 3-digit. So as a result, every time we have to deal with, say, 9 multiplier, it's replaced by 5. And how many stages do we have? We divide 9-digit to, say, 3 times 9 times multiplication of 3-digit. Then each 3-digit can be broken down into another 5 multiplication instead of 9. Therefore, as a result, the total number of multipliers needed in Toom3, so in Toom3, the total number of multiplier that is needed is just equal to, so number of multipliers. Multiplication, let's say in the sense of total multipliers of 1 digit by 1 digit, is 5 to the power log, and then you have n base 3, because every time we divide n into 3 digits. So this is the same as saying n log 5 base 3. And that's exactly the complexity we talked about for Toom3 algorithm. I hope that this example is helpful in terms of showcasing the generalized Karatsuba into an example of the Toom3 as one of the sub-cases for the divide and conquer fast multiplication or multiplication simplification algorithms referred to as Toom-Cook algorithms.